Okay, today, so last time we computed something for Versor algebra. Basically, we derived this Versor algebra, and today I want to talk about a little bit a more general thing, namely about the operator state correspondence and the operator product expansion in CFT. Yeah, so we started from the definition of CFT or any other field theory by path integral. We say that there is some machine that computes correlators, like correlator of O1, On is equal to the path integral in some basic field phi e to minus. Let me write the action of this theory as the integral over the manifold M of some Lagrangian of phi and d mu phi d to x, because it was the form of the action we had. And here we have this insertion of fields On divided by the integral d phi e to the same. So we can think about this as about such a sphere. Well, run a little bit ahead. So, and this object is called Z of phi. So here we have some points. And let us think about the following. So we can try to compute such integrals by cutting our sphere or some other manifold into several pieces. For example, into two pieces, or more. So let us imagine that we do something. Well, in this picture, let me do something like this. Let us cut it here and here, for example. So let us call this cut some L1, L2, well, maybe. Let me cut it like this. L3. Here we have all other fields. So uh, by this picture, I mean the following: that when we compute the integral and defy e2 minus L of integral of phi d mu phi d2x O1 On. So this integral can now be represented in the following way. So here we integrate over the field in all possible points. And when we choose some cuts of the sphere, it means that we first fix boundary values of this field at this cuts, and then integrate over all fields in this regions with fixed boundary values on this L1, L2, L3. So we write it, this integral as the integral. So let us introduce the following notation that phi on L1 equals to phi 1, phi on L2 equals to phi 2, phi on L3 equals to phi 3. So it's integral over d phi 1 and d phi 2, d phi 3. And now we write this action. Now so once we fix boundary values of this field on these boundaries, we can split this action into into four pieces that correspond to these domains. Let us call this domain D1, D2, or D0, D1, D2, and D3. We have this integral, and now let us write the integral over phi well, let me maybe, no, it's bad notation. Let me write it explicitly, that it's file 1, file 2, file 3. So it will be in the integral phi d0 in this domain with boundary conditions on L1. So phi on L1 equals to phi L1. So then there will be integral over phi in this domain d1 with two fixed boundary values, in the sense that phi on L1 equals to phi L1, and phi on L2 equals to phi L2. E2 minus, well, let me denote this S by S d0. So it will be S d1 integral over d phi d2 e2 minus S d2 and the same for d3. So is it clear? Okay, so now we can imagine that we compute this path integrals in over fields in D0, D1, D2, and D3. And what do we get? We get some, so these integrals remain. D phi L1, D phi L2, D phi L3, and let us denote these integrals by psi d0, which depends on phi L1, psi d1 that depends on phi L1, phi L2, psi d2 of phi L2, phi L3, psi d3 of phi L3. So what is written here is a kind of infinite dimensional multiplication of the integral kernels. So this psi d1 and psi d2 can be identified with some integral kernels. Sorry. Yes, I should have put it here. O1, O, sorry. So O1, O2, O2, O, O3, On. So here we should put probably O1, O2, O3, On. So something like this. So this things are integral. So is it fine? No. So these things are integral kernels, and these objects are functions in the space on which these integral kernels act. So, and you can say that they are wave functionals. So this one and this one. So this so this expression written in this form can be written as the following multiplication: psi d0 of psi d0, psi d1 O1, psi d2 O2, psi d3 O1 O3 On. Because we see how this works. First take this wave functional corresponding to the part of sphere with all the fields from 3 to n. Then we multiply it, multiply and integrate it with this kernel that depends on two boundary values. Uh, then do it again, and then compute a kind of scalar product with another wave functional that corresponds to this left cap. So there is such a way that allows us to rewrite path integral as a product of some operators between some states. And mm, this is quite useful approach because it basically allows us to switch to a quantum non-commutative problem of dimension of a smaller dimension, namely smaller by one, because this wave functionals we are working with are functionals of functions that live on a circle, and usually it is easier to study such things than original path integral. So and now what we see now we can call this space of wave functionals with some appropriate conditions that they are L2 in some generalized sense probably. But in any case, we can say that there is some reasonable space which appears when we try to compute such path integrals, and we can say that this psi d0 of psi d0, psi d3 O3 On vectors in this space, which is called the space of states. And this psi d1, psi d2, and the endomorphisms of H, or if we identify H with HU, we can say that they lie in H tensor H. So this is a space of a space of operators on H. So, and what do we see now? So are there any questions about this? So it is very natural to define vacuum in this space by saying that it is just such such a cup. So because if we take uh, some sphere or arbitrary surface, cut a hole in this surface and put this cup there, its position will be unnoticeable because it will just remove this hole without leaving any traces. So there is also a very natural object, this kind of a tube of some length. So it's important that all these objects have a complex structure. So it's not topological field theory, it's conformal field theory. Of course, everything is defined up to conformal transformations, but when we glue some things, then complex moduli are important. For example, we need to tell how to identify boundaries and so on. It means that if something has a complex a complex modulus, then it will affect corresponding object in field theory. So, namely, if this tube is it has size L, then it is well, we will learn later why it is so, but it is something approximately minus e2 minus L0. L is bad notation. Some x, then it will be minus x L0. It's an evolution operator. So if we so we can think about this as the following way. So suppose that we take so in some other coordinate it can be drawn like this. It can be drawn like so it is the same up to the exponential map. It is something that has an internal external radius r and internal radius e2 minus minus x r. So there is such a annulus with a modulus e to minus x. And if you take some sphere and insert this annulus there, it changes coordinates of fields. So, namely, if we start with a picture like this, some 0, z1, z2, z3. So we can insert this operator here, and it turns into the following picture. It will be 0, z1 e2 minus x, z2 z3. So and well, it's a bad picture. Sorry. Look like this. Here it's 0, z1. Here the sinus, z2, z3, e2 minus x, and here we have some radius, and here we have this radius times e2 minus x. So to insert it here, so suppose it was of radius r. We need first to cut this sphere along this circle of radius r. And then insert this annulus, then rescale internal part by the factor e2 minus x, because otherwise it will not fit. And then when we rescale it and it has the same circle in the boundary, we identify these two boundaries. So and we see that insertion of this operator scaled all internal points, but by the factor e to the minus x, and this is why it is called e to minus x L0. This is because it is precisely this scaling transformation. So 0 corresponded to scalings z to z times lambda. Check. So, are there any questions about this? Is it fine or? Okay, so this was about this simple objects. And now let us think about these operators that contain some oaths. First, yeah, so the first part of the title. So if we want to construct some state in this Hilbert space from the operator, how can we do this? So it's easy. We can just take some circle and put this operator in the center of the circle. Let me draw it here. And here we can take radius 1 for indefiniteness. So operators, local operators put at point 0 produce some states. And basically, so I uh, 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 I jumped a little bit ahead, so uh, let me say it like this. So local observable, because it is some further step to identify this local observable with mm, some with some operator acting on the Hilbert space. So if you want to construct some state, we can do like this. Just put this local observable at 0. Uh, State in this Hilbert space. Now, if you want to construct operator in this Hilbert space, so we simply take this cylinder, or maybe we can draw this cylinder in this way, and write and draw something like this. In principle, it is better to send the modulus of this annulus to 0. Otherwise, it will also contain some evolution operator. So basically, it is some operator of this kind, but with thickness going to 0. So we have identification of this objects, and now so we have some kind of triangle. And we know how to go in this direction. And we need to draw other arrows in this diagram. So the statement is that all these objects can be identified. When we go in this direction, we will actually need to take some infinite sums of local observables, but it makes sense if we think about uh, not just algebra, but its completion. If you allow infinite series and in some variables, basically like we had for OPs. So yes, so we need to draw the arrows in the opposite direction. Uh, this was one picture. This is another picture. Uh, so if you now have some arbitrary state in the Hilbert space, how to make it some operator? So there is psi in H. Well, so so I want to construct this arrow. No, sorry, this arrow. So there is some psi in H, and it can be represented as some disk filled in some way. Since it is just some arbitrary state in this space, and we cannot say anything specific. But and let us say that the radius, let us say that it is defined in the space of functions or on functions on the disk of radius r. So, and if you now want to make it to make it some combination of some combination of the local observables, we do just the following. We take sphere or some other surface, it doesn't matter. Put here some fields. So I'm basically explaining how to compute something with this local observable obtained from this state, and insert here this disk. But the radius of this disk should be lambda. And this lambda will go to 0. It is possible to do because we have conformal symmetry and all such scalings can be done. This is the place where conformal invariance is important. So if you do something like this, then we can uh, we can also scale it to make positions of all other fields of order 1 over lambda. But in any case, we will have some small parameter that describes the expansion around the situation when this insertion of psi is just 1 point. My statement is that this object will be some sum over so n, not necessarily over the integer numbers, but it starts from some negative value, not from minus infinity, lambda to the n, and so here there will be some zns, and the objects which we obtain in this series, zns will be identified with the correlators with insertion of some field O. Well, maybe let us use some notation. The ends some O n. So, or in other words, we can say that this wave functional on a disk of radius lambda equals to some lambda to the n O n. So there is kind of leading contribution which stays when we squeeze this disk to zero. There are some subliminal corrections, so we have in general all the series. And the simplest example of this phenomenon is the following. So imagine that we try to construct the state by putting this operator not at zero, but shifting it to some other point. And if we want to express it as correlators around zero, we just need to take Taylor expansion of this operator, and this Taylor expansion will be precisely this series. So in this case, these local operators will be just derivatives of O. So is it clear? So this way we constructed this arrow in the opposite direction. So So now we have this identification, and to close this diagram, we need to construct some arrow either from well, maybe the simplest way is to construct the arrow from this object to this. So let me think. So, well, the simplest way to construct this map is to say that if you have some operator acting on age, we can just act with this operator on vacuum. So, uh, we had some operator can be represented as some annuals in the sense that it can it should be glued to some boundary circle and give another boundary circle. So, and this can be identified. So it is let's call it L1, L2. Maybe, or maybe let me draw it like this as a cylinder. We can just act on vacuum. Maybe like this. For example, if this operator was some collection of insertions of local fields, then correspondence state will be just a state created by this fields inserted at this point. And if you start with some local observable inserted at some point, and so then correspondence state will be again the state created by this local observable inserted at some point, but now without possibility to act on something. So is it fine or not? Hmm? Yes, I wanted to compute such things for the case of free boson. Namely, in that case, we can compute explicitly such operators and see how all this insertions of fields act on the wave functions, or on the wave functionals. But how non-local? Like operators located at several points, or something from minus infinity to plus infinity? Operators that are located in some finite domain can be represented as a series in local operators because it is CFT and we have conformal invariance. So we can squeeze everything and say that there is this small parameter. For example, if we have an operator phi of x, well, in j of x, j of y, maybe it's better first to think without writing this path integrals and then go to the path integrals. Uh, so by the way, I forgot to say that OP that existence of OP also follows from here, because we can say that so. So we can consider some state that corresponds to that is created by two fields at z and 0, o 1 of 0, o 2 of z. Then we can say that it is some psi which lies in the Hilbert space. And then use this argument. Then say that it is a sum or z to power n is not necessarily a integer. Z to the n, some O3 of 0 ends. And by the way, you can notice that the only factor which we are using to prove existence of this OP is the existence of the scaling transformation and invariance of our theory with respect to this transformation. So all this works on higher dimensional CFTs, and they also have OPs. So we have such kind of formula, and let us see how it works in the applications. We actually saw such examples already. Uh, uh, so if we have some operator which is not at 0, if we have some O of z, then we can write it as sum over z to the n dn O of 0. It is about such kind of formulas. Uh, so one example. Another example about OP. So if you have some if you have some j of z, j of 0, then it will equal to. So who remembers the OP of j's themselves? No, y cube. So first of all, it is symmetric. So if it is j of z, yes. So and then normally ordered product. So it can be written as 1 over z squared plus sum from z. I forgot on factorial. Something like this. G of zr. So if you imagine that it is inserted that this combination of operators creates some state in this Hilbert space, then we just mm, expand this state into into the powers of z, and coefficients of expansions are states created by this field at zero. Mm. Well, and in general, if you have some collection of fields located at well, so if you have j of z1, let us write over everything in my scaled variables. It can be written as a sum of all possible parents. So some lambda to some power, product of z minus zi minus j. No, to some powers over sum of ji's, j's, some and then everything else can be expressed as a series in lambda around zero. So it will be sum of lambda to the k over k factorial, and then the operator of logarithmic derivative acting on all this. Let me think. Oh, maybe. Mm, mm, mm. So all this computed at zero. So basically trying to justify that formula. But at the moment, all these statements were about the operators that act on the Hilbert space, and the states in this space appeared just from the action of operators. And now I want to show some explicit computation which tells how this functionals can look like in some particular CFT, namely in the case of free boson. So let us try to compute the wave functional that corresponds to, in principle, arbitrary insertions of fields. So maybe can I erase probably this? So let us take disk of radius 1 and compute the path integral. So we have some phi here and phi on the boundary d equals to phi, call this phi b, phi boundary. And let us compute the integral z of j phi boundary equals to the path integral d phi with on this condition e to minus 1 over pi integral d phi d bar phi plus d2x plus integral j of x phi of x d2x. And to compute this, let us expand. So everything lives in the disk. So let us expand everything as a Fourier series, as a Taylor series. So namely, let us say that phi is a sum of phi and m, z to the n, z bar to the m. And the same for j. So one possible description of this state of this space of boundary values is by by fixing corresponding Fourier modes. So and let us also so let us first expand this this boundary value, if a boundary what is expanded as sum of phi n e to the 2 pi I e to the I phi n, where phi is this angle. Well, yes, phi is this angle. So clarify. And, then this field phi nm. Oh, sorry. Phi of z bar. So first, let us try to take into account this boundary values. So we can write that this is some restriction on the boundary of the following series. It is sum from n equals to 1 to infinity phi n z to the n plus phi minus n z bar to the n plus phi 0 phi boundary. So let us just take this piece here. So it will be phi 0 b plus some okay, plus some phi tilde of z bar. So I didn't write this in computation. I only thought about this, and did this and not so precisely. Mm. So mm, let us call on this part phi b of z bar. So a remarkable property of this phi b is that its Laplacian is zero. So phi b. And now let us use this to shift our path integral, to shift the integration variable in our path integral. And boundary values for this field will be zero. So maybe it's better to use here the letter z to make everything consistent. Okay, so we have this. It is just shift. And then we have e to minus 1 over 2 pi integral d phi b d bar phi b d to z. The cross term between phi b and phi tilde will vanish because when we integrate by parts, this phi tilde vanishes on on the boundary, and this field satisfies equations of motion. So we will have only the integral with phi tilde. And d phi tilde e to the minus 1 over 2 pi integral d phi d bar phi d to z plus integral j of z phi of z d to z. And now there are several questions. So first, suppose that we are computing everything with 0j. So in a sense, we are computing just vacuum wave function. Yes, and this will be given by this exponential of the classical action on this of this field phi b. And let's compute this. So minus 1 over, so 1 over 2 pi integral d phi b d bar phi b d to z equals to the integral d to z sum from n equal to 1 to infinity phi n b z to the n z to the n minus 1 sum of n equals 1 to infinity phi minus n b n z bar to n minus 1. So let me call this M because we have two sums and they will collide now. So, so the first question, what happens if you try to compute this integral for different n and m? What will it equal to? Integral is over the disk. Oh, let me write it. Absolute value of z less or equal than 1. Yes, yes, because z can be written as r e to the I phi. The bar is r e to the minus I phi. So the only surviving terms are with coinciding n and m. So we can write that it is 1 over 2 pi integral 2 pi r dr sum from n equals to 1 to infinity phi n b phi minus n b n squared r to n minus 2. So if you now compute this integral from 0 to 1 in r, will give. Also, who can tell the answer? So it is it is change from 0 to 1, phi n b, phi minus n b, n squared r to n over 2n from 0 to 1. So it is 1/2 sum from n equals 1 to infinity n phi n phi b minus n, right? So therefore, this um, vacuum wave functional mm, no, and, by the way, we can also notice that if this field is real, and it is real, then phi minus n is conjugate to phi n. So, so this can be written as a sum of absolute value squared. So this vacuum functional equals to minus 1/2 sum of n phi uh, phi n boundary squared same vacuum. Hmm? Hmm? But it is some number. If j equals to 0, so so it is for j equals to 0. So this is a vacuum wave functional for the free boson. Mm, mm. But now let us. Is it okay? So, and you see that even if it is, even though it is some function of the infinite dimensional space, a space of function, it is something quite well defined. It is Gaussian, so it's quickly decaying, and we can integrate some other or reasonable functionals of phi with this one. For example, polynomials, exponentials. So everything is everything will be fine. Mm. Yeah, but now the question is, what happens if we add some sources j? So. Hmm? No, we used just the definition of theory. So, in some sense, we used much more than just conformal invariance. We used that it is literally frame boson. for, 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 for quadratic theory, in a sense for the free theory. For a generic one with some potential, I have no idea. Mm, don't know if such calculations exist in any other case. Uh, mm. Yes, so if you do this, then you will need to modify this computation somehow. So this uh, this expansion will look like e to the phi e to the phi n times uh, mm, some Bessel functions. And then you will need to compute their norms and so on. Uh, Basically, you will need to find solutions of this equation, but with m squared on the right hand side, with uh, fixed angular momentum, with fixed power of e to the I phi n, and it will be given by a Bessel function. So in that formula, we will have norms of this Bessel functions, mm, and probably norms, and probably also something else, because we will need values of this Bessel functions at the boundary. Probably they will be not Bessel, but modified Bessel. Mm. So I never wrote this formula in the general case, but it should be something like this. So there will definitely be this separation between different momenta, and coefficients will be some numbers, probably some value of a Bessel function divided by or norm divided by value, something like this. Maybe everything expressed in terms of anyway expressed in terms of values of Bessel functions and their derivatives at this boundary. But and probably since we can get the answer, these expressions with Bessel functions should simplify to something rational, because we can find this function from starting from operator formalism, and it will be simpler, but mm, but definitely some doable exercise. And about other theories, I'm not sure that something like this exists even for Liouville, even though it is the simplest possible nonlinear theory. So. What people do sometimes, and they do so-called municipal space approximation. It is when they say that the only mode of phi contributing to the path integral is phi zero, like average value, and then they write a kind of quantum mechanics for this zero mode, but it is an approximate computation. Okay, so let's go back to this computation. So uh, so here we computed this vacuum wave function. But if you are interested not in the vacuum one, but in the arbitrary wave function, it is still very simple, because mm, here we don't have dependence on the boundary value. So it is just some function of j. It's a normalization. All dependence on the boundary value sits here. So uh, let us call this not z but psi. So psi of mm, j phi b equals to this integral. It's some constant that depends on j, and then it is e to integral j of z phi b of z. Would write it better. Let us maybe write it as this series. And times psi vacuum. Right? And now let us see what happens if we put some operators at 0. So where shall I write this? Probably I will erase on this example. So let us take z equal to I alpha two-dimensional delta function of z. In a sense, it vanishes at 0. So what will we get for this wave functional? Yes. Yes. So, and you see what happens. This alpha is this phi zero appears only in this exponential. This psi vacuum depends only on non-negative modes. And now we can see this phenomenon which you had before, that correlators vanish when the number uh, of when total charge is non-zero. So, namely, let us write this something like 5, 0. That it corresponds, and that corresponds to this operator. So we can check that now the integral in d phi psi e to I alpha 5, 0. Sorry, it is some bad notation. Let me write on this just this alpha delta of 0. Right B. So this integral in phi b splits into the integral in phi 0. Into alpha plus beta. So this will be just the norm, and this integral will be proportional to the delta function. Right? So, we see this charge conservation also from this point of view. That's fine. So let us think about some other fields. Namely, let us substitute J of Z equal to some nth derivative of minus d to the power n acting on this delta function. And then, in principle, let us take some arbitrary combination. Let us take some combination Cn minus d to the n delta n of z. So in this, and let us call it JC. In this case, in this way, functional will be so we will take this integral by parts, d to z. Maybe it's better also to divide this by n. Maybe 1 over n factorial. So if we integrate this, it will be some constant that depends only on g, on j, and then sum of Cn times pi times Cn, and let us divide also by pi. It will be sum of Cn times phi n from n equals to 1 to infinity. Psi vacuum of phi b. So if you now expand the left-hand side in Cn, so if you now expand the left-hand side as a series in Cns, then and do the same with the right-hand side, we will have something like this: that correlator of a path integral of so d phi e to minus s of phi dn1 of well, up to some constant dn1 of phi of 0 dnk phi of 0 will equal to proportional to the functional phi n1 phi n nk times psi vacuum of phi nb. So we see this operator state correspondence here that on the right hand side we have some arbitrary uh, polynomials of phi acting on this play vacuum. And also if we add this delta function at 0, we will have e to the I alpha phi 0. Let us maybe add this here as well. E to the I alpha phi of 0. Here we will have e to the I alpha phi 0. So we see that that arbitrary polynomial function times this psi vacuum can be written uh, as a polynomial function of derivatives of this field under the path integral. So it says that so the space of states in this quantum field theory is a space of polynomials. Actually, I didn't write anti-homomorphic variables here, minus n, but they are present. Uh, so arbitrary wave function is some polynomial times this exponential, and arbitrary operator is this exponential times some combination of derivatives. Maybe so we can take infinite combinations of such things, but up to this, this correspondence looks like this. So is it fine? That D and 1 phi of 0 D and K phi of 0 e to the I alpha phi of 0. So this is the local observable. Something that we can put under the path integral. This corresponds to the wave functional of this form. So this is in the space of states. So is it okay? Mhm. Uh, this we don't have this scaling transformation, so we cannot say that this that some wave function that lives on a disk of radius 1 is expanded as some series in powers of lambda of some operators sitting in the infinitely small disk. Because, for example, this might happen that you have some scale 1, and when you go to this 0 scale, let me think, if it's going to UV or to IR, like in which direction we are going precisely. But in any case, this might happen that there is some, for example, phase transition or Landau pole, or some asymptotic freedom when you try to go to that scales. So. mm, and this might happen that something happens at some scale, and so it does not make sense to write such expansions. So, no, in principle, operator expansions are used in the usual QFT, but they are understood only as some asymptotic expansions at the high energies. Uh, and as far as I know, usually we cannot say that there's some actual equality of functions. But in the case of CFT, just some series with some finite radius of convergence, which is defined by the local structure of this state. So is it kind of an answer on no, for massive boson, mm, for massive boson, probably it is fine to expand at small distances, but at large distances. So if you expand in 1 over r, we will have perturbative exponentials like 1 over r to the n, e to the minus mr. And if I understand correctly, what can be the problem in this case, that if you go to r going to infinity, this will be e to minus m over some z. So let us say that r is 1 over e. Then this will be e to the n, e to the minus m over e. So it's not a Taylor series. But in this case, it does not look like a big problem. Maybe maybe there is even no problem in this case. But if it is, for example, QCD, then I'm going to no. Let me think. Oh, maybe it's a similar kind of problem that when we consider asymptotics distance going to zero, it will correspond to asymptotically free theory, but this expansion will not work for distances higher than something. If you consider, for example, correlators in theory with confinement, they cannot be expressed in terms of correlators in the free theory at high energies. And here, well, here in principle we can try to write some series in mass, and if you take a large enough number of terms, we'll be able to reconstruct it. But mm, probably it's not even a pathological example. Yes, so maybe this computations with path integrals will be almost over. In the next time. And I will then use this formalism with pictures to formulate this computations we did in terms of vertex operator algebra. So, namely, this map will be this map in the vertex operator algebra that turns a state in the Hilbert space into the operator actor on the Hilbert space, and so maybe the only place where we remember about this path integral, I'll try to write the formula for this currents J as derivatives on phi boundary. So, so understand that for now we only know the action of this J's on the vacuum state, but we also have commutation law for them, and we can recover the action of other modes, negative modes, from that commutator. So, so probably also tell this. So, are there any questions? Okay, so thanks for your attention. See you next. Mhm. So, which operator? Can you say it again? Uh, which line? Closed, non-closed? Mm-hmm. Uh, so if you insert, you want to insert some integral, for example, of this current J, right? Here, right? Yes, if it shrinks to zero, if there is no operator sitting at zero, then it will be trivial. If there is some operator at zero, then they will interact somehow. Why to the same no? Why are they different? Ah, okay. Mm, you are saying about this map, right? Uh, no, uh, maybe I have to say that it works. Uh, so it is invertible uh, mm, for the operator that are some products of local observables and their derivatives. So if you take just some modes of these operators, then we can get something that goes to zero. So basically, whether it is zero or non-zero will depend on what prefactor we take. If we take something that has a pole at this cap, then it will produce some action of some mode of this operator on the vacuum. Otherwise, it will give zero. So if we integrate not j of z, but j of z times epsilon of z. Then if epsilon of z has a pole in this direction to the right, and then we close that hole, and then we will have a pole precisely in the middle of this mm, of this of this cap. So we will get some operator sitting here. So, for example, if we take here the integral j of z um, j of z over z dz, it will turn into j of 0. Acting on vacuum. Or it's the same as j minus 1 acting on vacuum. No, no, it's not zero mode. Yeah. And then so this vacuum has a zero charge, so it will act by zero. So, any other questions? Uh, uh, hmm? because we have this integral over a circle, and I wanted it to be one. But maybe it's too precise. I don't know. I just wanted this integral to give this combination, C and phi n. That's all. Because it's integral over the circle for radius 1. Yes, yeah, yes, and disk, but it's of radius 1, so it's area is pi. Maybe, no, no, it's fine. So if you substitute something like this, we'll get just science of science. Hmm? Mm, no, no. Delta function differentiates this science, and if it differentiates it to not to one but to something else, then mm, maybe. Wait, yes, I'm stupid. We don't integrate it after we differentiated everything. We just take its value at 0. Yes. So, yes, thank you. Yes, yes. They vanish not because we integrate over the disk, but because we take their value at 0. Thanks. Um, Other questions? Mhm. Mhm. Uh, no, states are defined on a circle. Yes. Mhm. Uh, well, we have yes. If you want to connect it to this disk, then internal radius should be 1. So we have complex structure which should be respected when we glue everything. Mm, You're welcome.